Okay, now let us continue with the revision on supervised learning or predictive models. Okay, the first predictive model we learn is actually the k nearest neighbor. Okay, in topic 4. Okay, based on the first revision, you should know it should be put in topic 5 as a kind of discriminative model. Okay, so logistic regression is also another kind of discriminative model. Okay, similarly for the decision tree, okay, which is in topic 7. Okay, and naive Bayes and LDA are generative models. Okay, so now let us start revising them, each of them. Okay, by the way, for your final assessment, you will see all of these 5 coming out. Okay, so make sure you have at least practice one example from each. Okay, so for KNN, it only takes in numeric features. Okay, and output is actually nominal. It has something called hyperparameters. Okay, the parameter which is not in the model but outside. Okay, where we can choose ourselves. Okay, so one is the K number of neighbors, and D is the type of metric. So the model is just if we give it a new data X, so the X will be put into the model, okay, to compare with the training data, and the K closest neighbor will be found, and the type of the okay in the type corresponding to the nearest k neighbors, okay, will be determined. Okay, the situation where let's say if k equals to 2, then if it's class 1 or class 2, then there is something like a undecided situation. Okay, so apparently in R, okay, it used a thing called L, okay, the minimum vote to avoid tie, to actually resolve this issue. So by default, if set to be 0, then most probably it will just pick the one of the class. Okay, if we set it to be 1, then it will require both. Okay, let's say k equals to 2, right? Then we have to have 2 in order to confirm it's this type, otherwise it's the other type. Okay, and so the KN in R, okay, is provided by the class package. Okay, it's relatively primitive because it only supports Euclidean distance. For final assessment, it's also just Euclidean distance, nothing fancy. KKNN, okay, some of you use it in the assignment, okay, but I think no one actually realized that the KKN is not exactly the K nearest neighbor that we have discussed in class. Okay, unless you set to the kernel to be rectangular. Okay, by default it's actually the weighted KNN. Okay, weighted means okay, because we have K nearest neighbors, but some neighbors are still slightly further away. Okay, some are closer, so it will give weightage to those closer, okay, to be higher weightage. Those are slightly further away to be having a lower weightage. the exact calculation. Okay, you have to read the research paper. Okay, where the researchers design this algorithm. Okay. Scikit-learn also provides something like this. Okay, under the sklearn neighbors. Okay, I think probably there are many more. Okay, for our course, we are focusing only on R. Okay, I don't have the time to actually cover everything. Okay, next is logistic regression. Is kind of a linear classifier. Okay, the linear part, okay, is actually associated with this. So it only handles the y when it's binary. Okay, normally the cutoff we will be taking 0.5. Okay, thing is a relatively simple model. Okay, we have the coefficients, and then when we do interpretation, normally we use the concept of odd ratios. Okay, so what kind of question could be asked? Okay, so most in any assessment, the model has to be given, the parameters has to be given. So either it's odd ratio, or the other one would be to carry out prediction, right? Okay, so prediction is based on the formula. Okay? Based on the formula, you just have to calculate the probability, and then okay, that's it. So in R, it's okay, it's a special case. Okay, the logistic regression is a special case of the generalized linear model. Okay, where the family is belonging to the binomial family. Okay, so a generalized linear model can support other types of problems that are covered in applied regression analysis. Okay, so type equals response will actually just give us the probability. Okay, so nothing more on logistic regression. Something okay, it's something rather simple, right? Okay. Okay, and in Python scikit-learn, it's actually supported under the linear model. Okay, I believe general linear model is also put under this category. Okay, next we are going into kind of generative model. Okay, the linear discriminant analysis. Again, this type of problems, the x has to be numeric. Okay, unlike the logistic regression just now, which can be for both numeric and categorical. Okay, but the categorical part is going to be a bit complicated when the category consists of many different classes. Okay, because okay, new variables will be created for each classes. Okay, so linear discriminant analysis and logistic regression are parametric models. Okay, we have parameters which we need to go and estimate. Okay, the model is rather simple with a posterior distribution, or okay, in this case, is the posterior distribution is related is the product of the conditional probability and also the prior probability. Okay, as mentioned during lecture, this kind of things are all calculated. Okay, whenever we product with small numbers, normally we take log, okay, to transform it to large numbers. Okay, and instead of multiplying small numbers together, we take log, and then we just sum the numbers. So the estimation of parameters is actually given in your lecture notes examples. Okay, the one used in the past year exam question is the so-called group covariance matrix method. Okay, we'll continue to use this thing. Okay, for calculation, just for you to get a feel of the complexity in parameter estimation. Okay, so I mean for this it's finding the mean, the prior probability. Okay, I mean this estimate is relatively simple. Okay, but the group covariance matrix is not. Okay, so for the group covariance matrix, you can either use R or what else? Calculator. Okay, if you are really good in the scientific calculator to find the inverse. Okay, the R library, which actually supports linear discriminant analysis, is called MAS. Okay, it's by default built into R. Okay, it has some it has two syntax for usage. Normally we use the second syntax by setting up the formula, but we can actually split the x and y. Okay, the explanatory variables. Okay, and the y is the response variable. Okay, so I think that's the kind of things I can set for LDA, right? Okay, unless you are given the parameters and you are asked to use them to find the discriminative functions, and then use the discriminative functions to decide on the classification. Next, naive Bayes. Okay, this is similar to the logistic regression. Okay, it handle both the categorical data and numeric data. Okay, and it's actually a parametric model. Okay, for categorical data, we are just going to use the categorical naive Bayes. Okay, and for the numeric data, okay, the approximation to be used is Gaussian naive Bayes. Okay, because naive Bayes actually assumes that all these features are independent. Okay, as random variable, they are independent. Okay, so we can just split them out. Okay, and perform the calculation. Okay, in lecture I just straight away multiply them. Okay, this you have to be careful when performing calculation using hand, because they can be quite small, and you cannot just simply round up to 4 decimal places and say, oh, everything is 0. Okay, that's not allowed. Okay, if you are not willing to write many decimals, okay, then you can apply take the logarithmic function on the numbers. Okay, and then in the end take exponential again to turn it back to the actual number. Okay, and in computer actually as always it will take log. Okay, so some of the limitations of naive Bayes is it's assuming that the explanatory variables are independent, but in actual fact it is not. Okay, estimation, okay, it's in the lecture notes, you should just study them and you should be fine. There's no Laplace smoothing, okay, coming out in the final assessment. Okay, so you don't need to worry about it. But you do have to know this concept because when we actually apply in real life situation, there are many situations where we just have to use the Laplace smoothing. Okay, so for the conditional probability, okay, I've already mentioned just now. Okay, so when the feature is continuous data, we just assume a normal distribution, so we have to use the unbiased estimate of the mean and standard deviation to perform the calculation. Okay, so these are the formulas. Okay, and for categorical naive Bayes, it's just a matter of constructing a conditional probability table. So okay, I think you have no problem with it. Okay, there are two main library for naive Bayes in R. Okay, one is called naive Bayes. Okay, the syntax is more or less like this. Okay, and as with all the models, it's always the algorithm. Okay, takes in the formula with the data. Okay, and then the model is trained. So this is a parametric model. The parametric model will be used to predict x. So we predict x, okay, given this model, and then we get the result. Okay, I think by default the type is actually just the class. Okay, another library in R which supports naive Bayes is E1071. Okay, so the syntax is just slightly different. Okay, more or less the same thing. Okay, if you want to take a look at the parameters, okay, we can use the summary to display. Okay, the very last model. What can be asked? Well, it's difficult to construct the decision tree as mentioned during lecture. So most of the time you will be given the decision tree and then just asked to use the decision tree to perform prediction. Okay, can we do that with this thing, naive Bayes? Yes. Okay, it's possible to that you get all the parameters and then you're asked to use the parameters to actually perform prediction. Okay, so okay, you already learn R part and 3 in the practical class. Others I did not explore. Okay, so if you want to know, then you just have to explore them yourselves. Okay, Python also provides decision tree, but in Python we'll find that many models actually has the corresponding regression version, okay, of all the predictive models we more or less mentioned here. Okay, in R, okay, I think it's true in Python as well. Okay, to visualize, we can plot it out. Okay, in R we have to label it using the thing called text. Okay, otherwise we just see the lines without any label and we don't know what is going on. Okay, the tree okay, and R part. And of course, this is mentioned, the information measures are mentioned in the lectures. Okay, so Gini is actually used in both the tree and R part, okay, because they all implements the classification and decision and regression tree, okay, the CART model. So okay, information gain, okay, it's also used in R part apart from Gini. So as mentioned in revision 1, we need to deal with the problem of overfitting. Okay, I mentioned that decision tree will most of the time be overfitting. So ensemble methods, okay, is ways to reduce overfitting. And in exam or assessment, normally the only questions okay, we can ask are philosophical, okay, explain roughly how ensemble methods like bagging, random forest roughly work, okay, or boosting, adaptive boosting, how does it really work. Okay, in general, they are very complex, so no hand calculation possible. So yeah, okay, so that's all for the revision. Okay, hope you are really good in calculation and be able to perform calculation for your final assessment. What else should I say? Okay, apart from that, I also require all of you to actually know some basic concepts. So there are small questions which is 1 or 2 marks, okay, maximum, something like that, okay, which ask you to compare various methods, state what are the differences and similarity between methods, okay, something like that. So